hysteresis. The effect of an external magnetic field on ferromagnetic materials is quite interesting. To study it, let us perform a simple experiment. Keep a rod of ferromagnetic material inside a solenoid. On passing a current through the solenoid, the magnetic field generated induces magnetic moment inside the rod. One can measure the value of the induced magnetic moment by an instrument called magnetometer. Knowing the volume of the rod, we can evaluate M, the magnetic moment per unit volume. We already know that B upon mu 0 minus M is equal to IF is equal to H, where IF is equal to current passing through unit length of the solenoid. This IF can be found from the current in ammeter and the number of turns per unit length of the solenoid. In this way, from the experimental values of H and M, we can evaluate B and study its variation with IF. The graph of B versus H can be drawn using the observations. One such representative graph for a ferromagnetic material, as shown at the point O in the graph, the substance is in its normal condition without any resultant magnetic field inside the substance. As H is increased, it generates increase in B. But this increase is not linear. Near point A, B is maximized, meaning it is the saturation magnetization condition of the rod. This process is not reversible. At this stage, if the current in the solenoid is reduced, we do not get back the earlier domain constitution, and when H is equal to 0, we do not get B is equal to 0. This means that when H is made 0, the substance retains certain magnetic moment. Hence, the curve AB represents the effect of reducing H. The value of B when H is equal to 0 is called retentivity or remanence. Now, if the current is increased in reverse direction, then at point C in the graph, the value of H for which B is equal to 0 is called coercivity. At this point, the magnetic moments of the domains are again in random directions, but according to some different domain structure. If we keep on increasing the current in the reverse direction, B goes on increasing in the reverse direction, and saturation magnetization is again acquired, but in opposite direction. After reaching D, if the current is reduced, the substance follows the curve DE, and again, by reversing the current direction and increasing its value, we obtain the curve EA. This process is called hysteresis cycle. The area enclosed by the BH curve represents the heat energy in joules lost in the sample per unit volume.